Before I start this video, let me take 30 seconds to tell you something about Exergic. Exergic is India's most trusted and most experienced institute for online GATE preparation. I am Chandresh Mahajan, founder and chief educator at Exergic. I am an All India rank 37 in GATE Mechanical Engineering, an ex-Indian Oil officer having 7+ years of teaching experience as of now. These are the GATE 2021 Mechanical Engineering toppers from Exergic. You can find their preparation strategy on Exergic's website. To know more about our GATE courses, you can visit our website or contact us on these details. Also, you can download Exergic GATE preparation app from Google Play Store. The link is available in the description of video. Have a look at this question of vibrations which is asked in GATE Mechanical in 2016. And please note, we are not trying to solve the question here. Okay, it's a very easy question, very doable question. Almost all of you will be able to solve it. I am going to discuss some of the variations and important concepts through this question, okay, which are not as such related directly to get the answer, okay, but to give you some learnings about how to approach the questions of vibration and some other tips regarding that. This question specifically says that the system shown in the figure consists of block A of mass 5 kg connected to a spring through a massless rope passing over pulley B of radius R and mass 20 kg. So this is having a mass of 5 kg. It is connected to a spring through a rope. This is the rope through which it is connected. Rope has been given as massless, important to note, right? So it's massless and inextensible. That was written, I guess, through a massless rope. Okay, inextensible is not written here, but you will see inextensible. This word will also be mentioned, inextensible rope. So with the massless, this inextensible, frictionless, these terms comes. Inextensible basically means that the rope cannot be extended, right? Which basically means that it's not going to act like a spring. In this question, we already have a spring present. So obviously this rope which has been given to us, it inherently is inextensible. We have a spring already which can be used to move the rope, right? But you will see some question, we will discuss them, where this term is going to be important, inextensible, okay? This is not that question, we will discuss that in the further questions. Passing over pulley B of radius R and mass 20 kg. This is having a mass 20 kg and radius R. Radius is not given to us. The spring constant K is 1500 Newton per meter. If there is no slipping of the rope over the pulley, this line is important, we will discuss soon. Find out the natural frequency of the system in radian per second. Okay, as I told you, I am not going to mainly discuss how to solve this question. I know it's an easy question. Majority of you will be able to solve it. I am going to vary this question. I am going to change some things in the question and then ask you that question. Basically, that's what I do a lot of times in the live lectures of Exergic. This question, which I am going to ask you next, after varying this, I discuss that in live lectures. And majority of the students get the answer slightly wrong, right? So let me come to the question that I want to discuss, that I want to ask. Keeping everything same in the question, spring constant is this much and there is no slipping of the rope over the pulley. Now my question is, in frequency analysis, tell me about which point, question number 1, about which point out of P, Q and R would you take the moment when you are going to analyze it. And question number 2, will changing the point change your analysis? Means if I choose to take the moment about P and then in the next approach while solving the same question I chose to take the point of moment about which I will take the moment as Q, will it change my analysis or not? These are my 2 questions. Pause the video and try to think of the answers, and meanwhile I am going to explain it. When I ask this question in live lecture, majority of the students say that about which point would you take the moment? some of them choose P, majority of them choose P, some of them choose Q, almost no one chooses R. Okay. And when I say that will changing the point change your analysis, in this some say yes, some say no, right? But mainly this is the first question is more important, that will automatically get you the answer of the second question. Look, whenever we get a question, we get a system which is in static system, right? I'm talking about any of the problems of mechanics. In those systems, whenever we wanted to take the moment, we could choose any point to take the moment, right? If this was a static system, suppose, and maybe I was asking you something, maybe how much will be the force in the spring, or maybe how much will be the reaction to this support, or reaction at this hinge. I have full liberty, I have full freedom, full choice. I can choose any point to take the moment. I can take this point, this point, this point, this point, this point, any point I can choose, find out the moment about that point, because and equate that to 0, right? Net clockwise and net anti-clockwise moments I can equate. I have the freedom to do that when it is a static system, when it is not moving, not accelerating at all. But the analysis that we do in vibration, that is not a static analysis, that is a dynamic analysis, right? We are going to consider the motion and the movement and the vibration, which is not a constant velocity motion. It is an acceleration. Continuously it's moving, stopping, moving in other direction. So it's a dynamic motion totally, right or not? In dynamic motion, what we do? We slightly modify the application of statics. We use the D'Alembert principle by considering the moment of inertia or the inertial forces, right? Inertial forces also. The point is that in the D'Alembert principle, one of the most important things which students miss is that when you apply the D'Alembert principle, you have to make sure that the motion you give to the body, the imaginary motion that you give to the body, should be similar to actual motion. I am repeating the line. In D'Alembert principle, in the dynamic analysis, right? We already have a complete unit on dynamic analysis in theory of machines. But this unit makes more use of it. Vibration makes more use of dynamic analysis, right? So when you are dynamically analyzing a body, you are applying D'Alembert principle in that system, which is not a static system, it's a dynamic system. What we do? We give a slight motion to the body, right? But please note that the motion that we give to the body, although it's not an actual motion, you can say it's a virtual motion or imaginary motion, but that motion should be similar to actual motion. What does that mean? That the imaginary, the virtual, the hypothetical motion that you give to the body should be coherent. Should be coherent or should be consistent or should be in compliance. So many difficult English terms, right? With the constraints. Let me explain that. Whatever constraints you have in the system, constraints means anything which is trying to move the body in a specific way or not allowing the body to move. Those are the constraints, right? This spring in a way is a constraint. This mass in a way is a constraint for the pulley, right? This hinge is a constraint. This hinge is ensuring that this pulley is not going to move randomly anywhere. It allows a specific type of motion, right or not? These are the constraints in this given system. Whatever hypothetical, whatever virtual, imaginary motion, slight motion we give in dynamic, in the vibration analysis, what we do? We slightly move the body, right? So whatever that slight motion you are giving should be coherent or consistent or compliant with the constraints. Means the motion that you are giving should not violate, basically all these words, what do they mean? That the motion that you are giving should not violate the actual constraints which are present in the system. It should comply with that, it should be consistent with that, it should be coherent with that, right? What does that mean? That in this case, suppose if I want to give a motion to the body about point P, okay, So what would that look like? About point P, I will try to turn it, roll it. So suppose this is how I have given a slight rolling motion to this, very slight rolling motion about point P. Now think that is this motion about P going to be compliant with the constraints, going to follow the constraints or not? If you look at this point Q here, if I want to roll this system about point P, Q point will tend to move up, right or not? This Q point will tend to move up. If I am trying to move it, suppose about this point P in counterclockwise sense. If I am trying to move it in clockwise sense, Q will try to move down. But is Q free to move up or move down or move right or move left? No, it is not. It is hinged at point Q. So if you want to give this motion to P, no matter you have the force of Bahubali, but you will not be able to roll it about P without breaking Q. You need to break off the hinge in order to roll it about point P, right or not? So are you following the constraints? No, you are not. Hinge is there. Hinge is saying that I am not allowing any motion in the upward or downward direction, but you are saying rolling about P. So you are trying to move Q up or down, breaking the hinge off, which is not allowed. You can only allow the rotational motion about hinge, right? That is why don't treat these problems like static problems. You cannot say that I can roll it about P or R or any other point. You have to comply with the constraints. The constraint, one of the very important constraints in this question is this point, hinge point, which means that about hinge you can rotate the body in either direction. Hence, in this question, when I ask you the question that about which point would you take the moment, you need to think that whatever motion I am giving to the body should comply with the constraints. So, I am going to give it a motion like this. About Q, it is rotating. Q is happy? Yes. P or any other point, maybe this constraint, what are they going to get? They might get elongated or compressed. Are they happy? Yes. Because you can extend or contract them. You can contract the spring. At this hinge, it's going to apply a force in the upward direction. That is allowed. Due to this rotation, mass will go in the downward direction. That is allowed. No constraint is getting broken. No constraint is getting violated. Very good. And this is something that you need to understand to visualize the questions of vibration. No matter what vibration question you are having. For example, have a look at this case. In this situation, you have been given this mass. Question is asking you frequency. Will you start vibrating this mass like this? No. Why? The spring that you have been given is not a lateral spring. It is a longitudinal spring, right or not? So obviously, in order to comply with this spring is made to sustain longitudinal oscillations. So the oscillations that you are going to give to the mass, small oscillation, will be along the springs. Right or not? You cannot give this oscillation to the spring and try to solve the question. If you want to do that, if you want to move it in that direction, you need to have such system where you have this rod which is going to resist the lateral movement, right? Any movement like this is going to resist, as you can see, as you can read the question. Question has given you proper deformable rod, right? Any such rod, if you move it up, if you move the mass up, it will try to resist that because that is applying some moment on this, right? They can resist such bendings, such deflections, right? Even question has said also, if the lateral vibration of the system, question is talking about lateral vibration only. So you are going to give it a motion like this, right? And not a motion like this now. Now you don't think that, okay, I am going to move it in the longitudinal direction because question has told you what constraint you need to follow. Similarly, this question also, what constraint you need to follow, you can think about it, right? Here, this mass can move up or down or it can move right or left also. But there is a hinge here. This hinge is not going to allow the motion like this. It can only allow a motion like this, right? So these things you need to check. All these questions which I am showing are questions from GATE PYQs, GATE previous year, which GATE has asked. And you can pick any other question also. Again, a question from GATE 2016. You have been given such a system, a spring is attached. What will you do? Will you consider the sliding? Will you say that no, now I am going to slide it? Or would you consider the rolling? Or would you consider both? You need to read the question for that. The disc is free to roll without slipping. Question has given you the constraint. That constraint you need to follow. You need to give it a rolling motion without slipping. Will that change the answer? Obviously yes. In this case, if you consider sliding or rotation, that is going to change the answer. Because if you are rotating it, it's a rotational analysis that you will do. Moment of inertia you will bring. If you are not trying to rotate it, obviously you are just sliding it like any regular mass. So simple inertia will come then. Moment of inertia will not be coming into the equation, right? The analysis will become translational and not rotational. But that depends upon how the question has been framed, what data has been given to you, how you can visualize the motion. Many such cases you can find. Another such question. Here also assume pure rolling of the disc. Question has given you. All these things are extremely important. Whenever you get a question on vibration, you don't just have to look at the data given, right? Many students just pick the data given, write down the data given and start solving. Right? Without being able to visualize the motion, how can you solve the question, right? Don't look at these simple questions. These are very simple questions, right? Difficult questions are also asked in GATE, right? And in general, you should be in the capacity to solve even difficult questions of vibration. I will discuss them in the later part of the video, of the lecture. So whenever you have been given question, you need to check the data which tells you constraints also, which tells you what motions are allowed or not allowed. Only then you are in a state to write down the equation and solve it. Without analyzing that, if you have a habit of just starting, you are waiting for a wrong question. If a question comes where analysis of motion is important and you don't have a habit of doing that, you are going to get a mistake in that question, right? Coming back to the analysis that we were doing to this question, out of P, Q and R, about Q, yes, as I told you, we can rotate. So the point about which we are going to take the motion is P and not is Q and not P and not R. And obviously question 2 got answered automatically. That will changing the point change your analysis? Yes. When the constraints are violated. If you are not complying, not following the constraint and violating them, then obviously it will change your analysis. You cannot do that. You have to comply with the constraints. Now, in this question, when we are trying to solve it, the learnings as I have written are not over yet. There are more things that I am about to discuss in the question. Now, if we start trying to solve this question, we are going to give a small, suppose clockwise theta rotation we have given. Okay, this is R. Small theta, I have exaggerated this theta. I have shown it very big, but you know it's very small, infinitesimally small theta. So small that it looks almost like a horizontal line, so small, right? I have shown it large here so that you can visualize it. You can rotate it clockwise, counterclockwise, that does not matter. Now, this force, spring force, is a linear force. It is not a torsional spring, right? We have torsional spring in the question also. It's a linear spring. So it will apply a linear force. Similarly, this mass here also accelerating will have a linear inertia, right? Not the rotational inertia. But this pulley, its mass is also given. Again, this is another important point to note here. That since mass of the pulley is given, its inertia is also going to get counted. This is another thing where question can trick you. In some cases, it may give you the mass or it may not give you the mass. Even if I look at other questions, for example, at this question, it is telling you the massless rigid rod. But if massless rod is not massless, if mass is given, then this rod also will be having a component in providing the inertia. Again, that inertia, that moment of inertia, you need to take about this point. You need to convert that properly, right? Small things to note. In which question inertia has been given or not given. If given in actual motion, if allowed, about which point it will try to move. Only about that point you need to take the moment of inertia while solving the question. So, in this case, this is having a rotational motion and it has a mass. So, it will offer rotational inertia. Now, in this question, to write the equilibrium equation, you have two cases of linear motions, one case of rotational motion. So, how are you going to analyze the system? Obviously, we will take the rotational motion equation. We will try to write the equation for rotational motion. Why? Because these linear motions can be converted to rotational motions about the center point Q, right or not? If you have been given a rotational motion, to convert that into a linear motion, it requires some additional analysis which may not get you to the answer. But if you have been given a linear motion, you can definitely convert that into rotational motion at that instant for that small value of theta, right? By having a distance r, a point which is located at some distance from the force, which may have a tendency to provide a torque, which may have a tendency which looks like it is trying to rotate it. So here, this force of spring, you may think it is trying to rotate the system about the center. It is a force at a certain distance r. Similarly, you have a weight at a distance r. You may think it is trying to rotate it about the center. Pulley obviously is rotating about that. It is hinged about that. So that rotation, you can say for all the components, this one, you can consider them to be rotating about the center Q, and then you can proceed and analyze the vibrations of this case, of this question, right? So if I give this small theta, this is r. So this length, small length, is going to be r multiplied by theta, right? Again, I am telling you, these theta I have shown very large. In reality, in analysis, we take such small values of theta like this. This is theta, right? So this and this length is going to be r theta, right or not? So for the case of spring, the spring force is going to be k multiplied by how much is its elongation, and its elongation is equal to r theta, right? Again, these are things which we have already discussed. So this is the force which is going to be resisted by the spring multiplied by the distance r. So this is going to give you the effective moment resisted by the spring. Inertial resistance, how much will be that for the pulley? Pulley is having I of mr square by 2, right? This is the basically J value of pulley, or Iz, right, about this center, Again, I am not going into detail of these things because we have already discussed them. So this is for the spring, or rather, right? So for the pulley, the moment that it is going to offer is going to be I of the pulley about this center multiplied by theta double dot. So this I is mr square by 2, this is this value of r, and okay, this m is capital M, this is not small m, this is the capital M. Capital M is representing the mass of the pulley, small m is representing the mass of this block, right? And now for the block, what to do? For the mass for the block, what we need to do? That mass, as I told you, if you look at that independently, it is performing linear motion, but here, since we are analyzing the system about the center, what it is doing? It is performing for that theta distance a rotational motion. So rotational moment of inertia, rotational mass moment of inertia we are going to consider for this mass about the center. It is at a distance r. So how much will be that value? mr square by 2, right? We have a center, we have a mass m at a distance r, trying to rotate about this point. Its mass moment of inertia is mr square. So that's what we have written for that mass multiplied by theta double dot. Now since this spring will try to bring it back, spring will always try to be on its natural length. This is going to offer inertia, always resist the motion. This is also offering inertia, always resist the motion. So in this situation, all three of them are trying to act in the same direction. So we have equated all three of them and put them equal to 0. Please note that since the mass, this pulley and this block, both of them are offering a moment of inertia, mass moment of inertia. So this equivalent value can also be called as the equivalent mass moment of inertia for this system. These are the different components of this system. So this is the equivalent value for the combined system, for the combined components, right? Very simple. Writing this equation is very easy. We have done that already in many cases. We will do that in many other coming cases. So from this, the angular frequency is going to be root k equivalent, which is kr square, divided by root mass equivalent, which is mr square by 2 plus mr square. Now r square all going to get cancelled. The value of k is 1500, the value of capital M is 20 by 2, 10 plus small m 15. So root 100, it is going to give us 10. This value is going to be 10 radian per second, which is the answer for this question. If you look here, all the r squares are getting cancelled, which means directly that the angular frequency for the system is not going to depend upon the size or rather radius of the pulley if you keep its weight constant, right or not? And this is an important learning. Please note that these things can be asked like a question to you. By giving such a system, it can easily frame a question. It can frame a MSQ also, where it can frame an option that the angular frequency will be independent of the radius of the pulley, right, for a given mass, which makes sense, which you can check from here, r square getting cancelled. These things you should be ready for. These things, these types of variation in the question, you should be ready for. In fact, there can be such questions also where the complete component given to you may be redundant. For example, here in the same question, if I attach, let's say a spring here, will it make any sense? Will it make any contribution in this motion, in its oscillation? No, not at all, right? So there can be such redundant components also, a redundant spring component, a redundant damper components. They can be there in the questions. Although GATE is not very keen on asking those questions so far, but since the quality of questions that are asked in vibration is going up, you should be ready for such types of questions as well. Now please note, whenever you are solving these questions, there are many places where silly mistakes are possible, right? Especially in mass moment of inertia, when to consider, when to not consider, about which point to consider, right? In taking the moments, in writing the equations, in considering the weights, many such silly mistakes are possible. But if I broadly talk about the steps required to solve the question, there are mainly two steps. One step would be to look at the problem, to visualize the motion, visualize the actual motion if allowed, right? Being okay with all the constraints, and write that in the form of equation, right? This is one important step in majority of the question. And step 2 would be to identify the different systems given to you in the question and how to relate those systems together. This is something that is not required in all questions, but in some question it can be required, especially in the good questions. For example, if you look at this problem, it's a problem from GATE 2020. It was a highly discussed problem, and it's a good question, a brilliant question, where you may be required to identify the systems and relate them together. So while solving the questions of vibration, not only visualizing, obviously that is important, but not only visualizing the motion is important, but also you should be able to identify the systems and relate them together. And this is something that we are going to learn in this next question. Let us discuss this.